Thank you and good afternoon, everyone. Today I'm going to share with you about some of our work from this project, which is a collaboration between University of Southampton, Plymouth University, and Greven Hoverwork. We have been looking into these two device variations, both sharing the same principle, which essentially it has a deformable bag enclosing a volume of air, and under wave action the bag expands and contracts, pumping air into and out of a second volume through a turbine. And the difference between this and that is that the SQ1 has a bag that is piercing the free surface, whereas the SQ3, the bag is completely submerged and it has a rigid float, which here is a cone. We have done two series of tests for SQ1. The first one we did was last year, and it was focused mainly on pump oscillation test, where we drive the device in still water, forcing it to heave and radiating wave. And the second series was mainly on estimating the power capture in regular wave. And in model scale, in order to get the compressibility correct, we have to provide additional volume, which can be quite large. So in the setup, we have a flexible hose coming on top of the bag, which come into an additional volume to represent the volume enclosed by the bag in full scale. And one thing we discovered during our first test is that it is possible for the bag to have two different shapes for the same pressure, which is quite unexpected. But then we were able to confirm this numerically as well. And these are just the videos showing the device pumped in still water. As you can see, these are the two possible shapes for the same pressure. But note that the amount of air in the bag is different, although the pressure is the same. And this is our recently concluded test. Here you can see the device and the power takeoff, and we use 3 air tanks, each with a capacity of 1.1 meter cube, and we have 2 valves which we can open and close to investigate the effect of different volumes for V1 and V2. And there is a photograph of the setup. You can see the PTO here is a series of capillary tubes and the 3 air tanks. And this is the device in water. And one of the things we did during our recent test is to investigate the effect of having mooring lines, which was used to limit the pitch of the device. Here, as you can see, the mooring lines were taut, and the device is not pitching a lot. And here, the mooring lines were slack, and you can see the pitch is quite significant. And it is interesting to see that limiting the device in limiting the pitch of the device actually give a higher power absorption, and it is seen quite consistently across the different cases here. The circles are with the moorings loose, whereas the crosses are with the moorings taut. That is, the device is restrained to heave only. And the difference between these two slides are the effects of V1. Here the V1 is larger. As you can see, the period is longer. And when V1 is smaller, the period is shorter. But again, when the device is allowed to pitch freely, there is a reduction in power capture. And this is the test of the SQ3, which we did earlier this year. You can see a more dramatic motion of the bag, since the ballast is oscillating quite a lot. And here we compare the capture width of SQ1 and SQ3, scaling it up to full scale, assuming a model scale of 1 to 20. The circles are the capture width of SQ1 and the crosses are SQ3. And these are the different dimensions of the device in full scale. As you can see, SQ3 has a lower capture width, although it's a bit broader, but SQ1 has a higher capture width, although the volume of the second volume is double that of the SQ3. And now I will talk about our numerical modeling. First, we have to have a method to predict the shape of the bag in still water, and to do that we make several assumptions. The tendons are inextensible, that is the red line here, and the tension is carried by tendons only, not by the membrane. And these are the two possible shapes for a pressure of 0.4 meter of water, and we have predicted this numerically, and you can see a reasonably good agreement. And then we developed a frequency domain model to simulate the pump oscillation case, that is forcing the device to heave in still water. And we use this equation of motion. And for our model, this is a simplified model. We consider only heave and axisymmetric deformation of the bag. Hence, there are only 2 degrees of freedom. And for the deformation of the bag, we need to select a mode shape. And this is obtained by taking the difference between 2 static shapes of the bag obtained under different pressures and different elevation. As you do that, you can separate it into radial and vertical component, and this can be input into WAMIT together with the geometry, the mean geometry of the device, and WAMIT can calculate the added mass and radiation damping, and you can solve this equation of motion. So here is our numerical prediction compared to the experiment. There is some slight differences here because this is a simplified model. And when we plot the amplitude of the top of the bag for different cases, these are with different amount of air in the bag, case 1 to 5. This is with case 5 is with the bag higher in the water, the bag is tighter, whereas case 1 is with the bag lower in the water. As you can see, the numerical prediction, there is some disagreement in the resonance period. But we have also developed a more refined model where we discretize the bag into many small elements. So there are multiple degrees of freedom. And as you can see, the agreement is better with the experiment. So as a conclusion, we have confirmed by experiment and numerical modeling that SQ1 has longer natural periods than a rigid device of the same shape. But the natural bandwidth is also narrower because it is compressible, so it doesn't radiate as much as a rigid device. And then we can possibly tune the device using two different ways. First, by varying the amount of air in the bed, and also by varying the size of the compressible volume, which was done in the test by opening and closing the valve connecting to the V1 air tank. And for SQ1, two bag shapes are possible, which have the same pressure. But for SQ3, up to 3 bag shapes are possible, which have the same pressure. And we are still working on improving our 2-degree of freedom model and extending our multi-degree of freedom model to include incident wave cases. Thank you very much.
This production is brought to you by the University of Edinburgh.